Hello and welcome back. This is the second part of heat and temperature. It's called Lecture R here in the course. Keep in mind that our focus here is just the concepts, just the science behind heat and temperature. We try to avoid as little math as possible, but there will be a little bit of math today. All right? The first thing I want to talk about is calorimetry. Okay? Now that word comes from the calorie, and we learned that a calorie is the amount of energy needed to raise 1 gram of water exactly 1 degrees Celsius. Okay? And so, where's my pen? Here it is. Calorimetry uses the properties of water and its known specific heat to measure the amount of heat given off by different processes. In the lab today, we are going to be analyzing the number of calories in one of these marshmallows. On the information label here, it tells you that there are 100 calories that are contained in a serving size of about 30 grams. Okay? What is that? How is that obtained? How is that, where does that come from? How do they know there's so many calories in here? I mean, it doesn't feel hot. So calorimetry is the process by which we actually burn substances, for example, a marshmallow or a fuel or something. It heats water up, and based on that increase in temperature, we can do some calculations to figure out how much heat was absorbed by the water, and therefore how much heat is in a 30 grams of marshmallows. And remember, heat is thermal energy or energy, okay? So it uses water, which has known properties, and if we warm up the water by a chemical reaction, for example, we can know exactly how much energy was released by that chemical reaction because it warms up water. So remember again that 1 calorie, this is a unit of energy, right? This is energy. All right, when you're feeling low energy, you need to eat a candy bar or something to get your energy back, right? This is the same kind of energy we're talking about. There are sugars in the marshmallow that have particular chemical bonds that when it's metabolized by our body, releases energy, okay? So 1 calorie is the amount of heat or energy needed to raise one gram of water by 1 degrees Celsius. All right, this is review. We've talked about that in the last lecture. So some people call this the MCAT equation. Now let me tell you what it is, okay? This is heat or energy. This is mass. C is a constant. Now for water, the constant is 1. There's 1 calorie of water, 1 calorie that is equal to 1 gram of water that's raised by 1 degree Celsius. Okay, so this is a constant. Different substances have different constants. They're called the specific heat constant, and we are not going to talk about that. Okay, but if you want to warm up lead or iron or a piece of wood or a cement block, it's going to have a different number here. And this whole term right here is called the change in temperature. Okay? So 1 calorie is equal to 1 gram times this constant, which for water is 1, And if you change the temperature by 1 degrees Celsius, your change in temperature is 1. So 1 is equal to 1 times 1 times 1. You can see how this works out. Now let's do this for some different numbers here, okay? I have a balance, and I have some water in here. It's zeroed out and ready to go. That's 90.09 grams. Remember that grams is a mass. And we use symbol M to stand for mass. Now, I want to measure the temperature. So remember how we do that? We do that with a thermometer. I think I'll do it with a digital thermometer because you can see that on the video a little bit better. And of course, we're using scientific units here, and the temperature, well, it's changing a little bit here as it's equilibrating with the water, but I'm just gonna write down whatever this value is, 21.9 degrees Celsius, okay? All right. Now remember how we indicate the units for temperature? It's with that little circle that's superscripted, that means degrees, and the capital C means Celsius, all right? And now what we need to do is warm this up. In the lab, we'll use a marshmallow, but here I'm just gonna use a Bunsen burner, which provides a tremendous amount of heat in a very short amount of time, okay? So let me see if I can get this camera set up here without it falling over or anything. Well, that looks pretty good. Okay, so this is, in my hand here is the Bunsen burner, and I've got this little lighter that provides some sparks. And you can ignore all this other clutter here on the countertop, okay? So here's my Bunsen burner. It's not lit yet, okay? I'm gonna turn on the gas here, and it's lit. We've talked about combustion reactions before in chemistry and how they produce light and heat generally and tremendous amounts of heat. Okay, this is very hot. Now what I'm gonna do is I'm gonna put the beaker filled with that amount of water here, and I'm just gonna heat this up, okay? For a little bit, a few minutes, okay? Now, what's going on here, remember, is that there's a conservation of energy. This combustion reaction is releasing heat, and a lot of it's going to the outside environment. I can feel it warm out here, so it's heating up a lot of the air. But a lot of that heat is going into the water to warm up the water. And remember, to warm up water, it has to absorb energy, absorb heat, okay? So we're transferring heat from this combustion reaction to warming water up, all right? I'm gonna turn this off now. I think we'll get the idea. And we're gonna go ahead and measure the temperature here of our warm water, okay? As with all thermometers, you need to wait a little bit for it to reach what we call thermal equilibrium. It takes a while for the heat to transfer to the stainless steel and actually warm up the thermistor inside. And finally, when everything is the same temperature, this number will, stay constant, okay? Usually it takes a minute or so, and I don't want to waste our time here on the video. So I'm going to write 37.3 degrees Celsius, okay? 37.3 degrees Celsius. Let me see. what did I say, 37.2 degrees Celsius. Okay, so let me try to fix this leaning a little bit there. Okay, so to calculate the change in temperature, you want to calculate this difference, okay? So this is the final temperature and this is the initial temperature. So again, there's a little bit of math here, but follow along. So we're going to take the higher number here, 37.2, and subtract the lower number, 21.9, and our change in temperature is 15.3 degrees Celsius, okay? So the change in temperature is 15.3 degrees Celsius. Now this will only work in Celsius. And in our mathematical equation before, we called this delta T, okay? So the mass is that, we got it from the balance. Our change in temperature was obtained by these two temperature readings with our thermometer, okay? We had cold water and then we had hot water. And now we remember the C, or the constant, is 1, okay? And that's for water. Please don't confuse that C with calories. Please don't confuse that C with degrees Celsius. That is C, smaller case, lowercase c, and that just stands for the constant, okay? So we're ready to go. We have the three quantities here, and what I want to do is calculate how much heat was actually put into that water to warm it up, okay? So I'll change pen colors here. So here's our Q equals MC delta T. It almost looks like MCAT over there. And so in place of each one of these symbols, we want to put our numbers, okay? So 90.09 grams times, our C is just going to be 1. So, you know, on our calculator, it's very easy. You're just going to multiply by 1. Now you've got all these units. In this class, we didn't talk about unit cancellations, so just focus on the number parts here for now. Bear with me. And then we have 15.3 degrees Celsius, okay? So we've got our mass of water, we've got our constant, we're heating up water, and then we have the change in temperature. So with our calculator now, we can take these numbers and multiply them, okay? So 90.09 times, we're just going to multiply by 1 here, right? Which means the value doesn't change on your calculator. And then multiply by 15.3. And what you get is a result like this, okay? 1,378 calories. Okay. Calories is abbreviated CAL. Okay, so that's calories or cal, okay? So that's how much heat we put into warming that water up, you know, about 15 degrees Celsius. Now again, it's going to depend on the mass. So if you have more mass, it's going to take more energy. If I have cold water in a water heater and I want to warm up 40 gallons of water to a nice temperature so I can take a warm shower, it's going to require a lot more heat because I have a lot more water. If you want to warm something up to a higher temperature, that's also going to require more energy. So, for example, we warmed up this water to about 37 or so degrees Celsius, and it's not too hot. But if we wanted to bring this to a boil, which is 100 degrees Celsius, it would require a lot more energy to get that up to that higher temperature, okay? So please don't worry about the math and plugging in numbers. Please focus on the concepts here, okay? So if you have a greater amount of water, it's going to take more energy to warm it up. If you want to warm it up to an even higher temperature, which is the change in temperature, it's going to require more energy. Okay? So that's the basic idea behind this concept, okay? Now let me talk about heat flow. So this is switching gears a little bit here. The first concept we have, there's 3 different types of heat flow. The first type is called conduction. Let me see if I can find this over here. Well, I'll just use this. This is a fairly large diameter aluminum rod, and aluminum is a metal, it's a conductor. Remember how we classified elements in the periodic table as metals, which are conductors, and non-metals, which are insulators? Well, this is aluminum, which is a metal. It's located to the left of the periodic table, and left of the staircase in the periodic table, right here on the periodic table. And it's a metal, it's metallic, it has shiny appearance to it, it conducts electricity, and it also conducts heat. Now, if I were to put this in a fireplace and I were to heat the end of this, eventually the heat would travel through the conductor and reach my hand, and then my hand would start feeling hot and I would have to drop it, okay? And that's called conduction. What's happening when you have conduction is that molecules, when they're in the fire, begin vibrating more quickly, okay? But this is all one solid material, so molecules will bump into other molecules nearby, actually aluminum atoms, right? So atoms here will start vibrating quickly, bump into other atoms, and then those atoms will bump into other atoms. And then eventually, because of molecular motion or atomic motion, the atoms of aluminum, which are moving very vibrating in all different directions and so on, will eventually bump in and cause other molecules nearby to begin moving quickly, and then that's why the heat will conduct down a conductor. Now remember, heat is nothing more, temperature is nothing more than molecular motion or atomic motion, okay? So the energy of motion is heat, okay? And that thermal energy is transferred down this conductor, okay? So that's usually done in solids, okay? And if you have an atom that's, wiggling and jiggling, eventually it'll transfer its motion to the right where this motion is not moving, okay? The second type of, and that's usually with conductors or metals, okay? So metals conduct heat. And this is why your pots and pans are made of aluminum. Okay. This is an aluminum pan. Okay. And when you put this on the stove, whether it's gas powered or electric powered, it very quickly heats up the pan, and heat is transferred across that barrier to your water, which can then boil and you can do cooking, all right? Things that are not good conductors are ordinary glass, wood, ceramics, things like that. And that's why your coffee mug, for example, I don't have one at the moment, might be ceramic, okay? Actually, I do have a coffee mug. Let me show you. It was a good excuse to take a sip of coffee here. So this is a Starbucks cup, and the cup is made of paper, the lid's made of plastic, and this coffee collar here is made of 2 pieces of cardboard. You can barely see it in the video, but there's an air space in between it. Air is an extremely good insulator, and this is why you wear a jacket, all right? The outside air can't excite air molecules very well because they're so far spread apart, okay? You see, in a metal, the atoms are very close to each other, so if one starts vibrating, it's gonna bump into other atoms very easily, and the heat's gonna conduct very well. So metals are a very good conductor, but air is the opposite of that. It's an insulator. If you're ever homeless or something like that, one survival technique for surviving in the winter is to find some newspapers and crumple them up, not very tightly, but very loosely, and just put that under any old shirt you have or whatever you're wearing, and it will bulk out your shirt and it will provide air, which is insulation, okay? So insulators, like air, do not conduct heat as well. And this is why ski jackets are very bulky. They look kind of fluffy. You can't really invent a really good ski jacket that's gonna look like my shirt, very thin, okay? There's just no way to do that, not now. The best way to do that is to have an insulator of air, okay? So that is how heat flows, usually in a surface, like a piece of metal, okay? Now, the second type of heat flow is called convection. You may have heard of the idea of a convection oven. There's actually a fan in there. You may have heard of the idea of an air fryer. It heats up an element, and then there's a fan in there that blows hot air around, so it heats your food much more quickly. And also, if you have let me show you. This is a typical heater. Okay, you can set the, kind of hard to hold, it's so big, but you can set the temperature on this side, okay? And there's some grills in the back that take air in. It passes over the heating element that's here, and it blows the hot air out into the room that you're trying to heat up. That's called convection. Convection is the massive movement of large amounts of air using a fan, for example. Okay. So air fryers, convection ovens, that thing is called a space heater. Because it's designed to just heat up a small space, like your room or a closet or a basement if you're working in a very cold room. Okay, all of these use fans, and the idea here is that you can have hot air that can be moved to different parts of the room through convection. Now, sometimes convection is a natural phenomenon. So if you have some ground and then you have the sun, right, warming up the surface of the ground, the hot air is going to rise because it expands, it has lower density. Okay? So it rises up, and then cool air is going to come in, right? So if the air leaves that location, it has to be filled by something else. So cool air is going to come in, hot air rises up, and so you can get convection currents that kind of go in a cycle, okay? If you look at the planet Earth, there's a lot of different you know, cells basically, where there's convective cells in the atmosphere, where there's air moving in circular direction in the northern atmosphere, or anti-clockwise basically in the southern hemisphere of the Earth, okay? So this right here is just a natural type of heating that will cause air currents, okay? So all of these require currents of air. You can also do that in liquids, okay? So if you have a large swimming pool, maybe you're looking at this sideways here, and then over here, usually if you look at a swimming pool, there's some pumps and filters and things like this, and you'll have something that kind of looks like a water heater. It heats up the water and makes hot water, and then it will pump this back in, okay? Maybe on the opposite side or something like this, okay? And then this water will slowly flow and mix with the other cold water, heating it up a little bit. And if you kind of have a cold pool, it's enjoyable to stand right by the outlet of one of these heaters. You feel the hot, you know, water kind of splashing on your back, and you feel like, oh, a little bit warmer, okay? But over here it might be cooler. All right, so water is also a fluid. Water and air can both be moved by fans or vents and flow and mix in that fashion, okay? So this is all convection. We normally don't think of solids as undergoing convection, all right? Because they don't move, they're just solid, right? The third type of way that heat is transferred is through radiation. This is called radiative flow, or radiative heating. And there's different applications of this. One of them is a heat lamp, okay? If you go to the buffet, or maybe you have eggs that you want to hatch for chickens, right, in the spring, to have some chickens on in your property, on your house, on your farm or something, you put the eggs under an incubator lamp. It's kind of a reddish color, and it gently warms the eggs so that they stay at the right temperature until they're ready to hatch. It's also found in the buffet. So you go to different food places, and sometimes there's food there underneath some special lights that are designed to keep it warm. And these are sometimes called infrared lights. Or heat lamps, okay? And it's a form of invisible radiation that gives off heat. Our bodies are warm-blooded, and we are always giving off heat, okay? And this is the same kind of radiation, okay? And if you have a fire, okay? I'll just demonstrate with my hand here, but we were talking about this previously. If I heat this up in a fireplace, and then I put my hand close to it, I can kind of feel that it's warm. I shouldn't touch it, right? So if you want to know if a metal object is really hot or not, you don't touch it because you might burn yourself severely. You put your hand close to it, and then when you feel the heat, you know that it's hot. That feeling is infrared radiation that's coming off that object. We feel the heat coming up from the ground on a hot day. So in the summertime, if you go to your car and it's all metallic, you know, and then you walk up to the car, or you're about ready to touch the car, and you just feel that it's hot. That's a form of radiative heating or radiation, okay? So heat lamp, infrared lights, hot car, a human body, hot piece of metal. These all give off heat in the form of infrared radiation. IR stands for infrared, and we learned that it's a type of radiation, electromagnetic radiation. One of the things I've noticed is that firefighters, they wear kind of like these silver protective gear. They also have something called an emergency blanket, and all it is like this piece of plastic that's aluminized on one side. It's a mylar sheet that's aluminized. So basically you're wrapping yourself with aluminum foil. How does that work? Well, you know I'm not very good at artwork, so I'm just gonna wrap this individual with a piece of aluminum. Okay. So here's aluminum. Okay. And this is your emergency. They call it a blanket, but it's thinner than aluminum foil, okay? It's very thin material and it's plastic. See, it comes in a small pouch, and if there's an emergency, you unwrap it and it kind of makes a square, a rectangular sheet, and then you can wrap this around yourself. And what it's designed to do is reflect infrared radiation. So your body gives off infrared radiation, as we mentioned. When it reaches through the air, when the radiation goes through the air, right, it bounces off the aluminum and comes back to you. So it holds the heat inside of your body. A firefighter will have an aluminized, maybe they're fighting a fire with a fire extinguisher here. And so I'll use red. I know red can't show up very well, but here's your fire, okay? And a firefighter is spraying fire retardant or water onto a fire, okay? Now, if you stand close to a fire, you feel the infrared radiation heating you up. It feels very hot, so you have to stand further away from it to feel comfortable. If you're too close to a fire, it can burn you, it can feel hot, and cause you blisters and burning, and even though you're not touching the actual flame itself. Same thing when you're fighting a fire. We have this huge building on fire, so that's an enormous surface. And what's coating the outside of the firefighter's protective gear is a shiny aluminum, okay? And what that does is it reflects infrared radiation. So the fire will reflect off of the aluminum. The infrared radiation that's produced by the fire will reflect off of the firefighter, so they'll feel a little bit more comfortable. You can see these sorts of aluminized coverings on different spacecraft, James Webb Telescope, for example, the International Space Station, and other satellites and things like that, okay? Say there's a sensor that's out there in outer space and exposed to sunlight and it needs to image Earth or something, but it can't heat up a lot. So what they do is they wrap the outsides of that with a gold foil, usually it's nice gold, right? Or silver or aluminum, something like that. So it reflects infrared light off of the camera or the optics or whatever, so it keeps it nice and cool for operating, okay? So those are the three different types of heat flow, okay? We've got conduction through solids, convection through air. For example, I can have a fan that blows hot air to that side of the classroom, and you have irradiative or radiation, okay? Radiation is nothing more than infrared heat, okay? And you can feel the heat. That's what we're talking about. You can feel the infrared radiation coming off of a hot surface. All right, next I want to talk about phase changes. Phases or states are just the solid, liquid, gas we've been talking about, okay? All right, solid, liquid, and gas. Now, we distinguished how these are different. Solids, the atoms or molecules are more tightly packed, and a liquid, they're still packed, but they're loosely held together and can move, and gases, they're very far apart, right? So solids, generally speaking, are better conductors. Gases are generally insulators or not conductors, okay? Usually, the particles in a gas are moving very quickly. They're chaotically moving and bouncing off of a container. We generally think of liquids as moving more slowly, and solids maybe even moving less slowly than that. Okay, the atoms themselves might be moving less slowly. But it's a better idea to think about the degrees of freedom. In a solid, atoms are jiggling. In a liquid, they're flowing over one another and moving. And in a gas, they're tumbling, moving, and bouncing very chaotically against the container walls. Okay? Now, when a phase change occurs, the energy increases in the system because you have to add heat. Okay? Heat is needed. Okay? That means we add heat to the system. For a phase change from solid to a liquid. When a solid changes to a liquid, in everyday common language, we call that melting, right? An ice cube melts, it changes from a solid cube-looking object to a puddle of water, right? In chemistry and physics, we call this fusion, okay, fusion. So this is the ordinary English language term, and then in the sciences, we call it fusion, okay? And we have this idea of the latent heat of fusion. If you take ice, which is an ice cube at 0 degrees Celsius, okay, and you add heat to it, this material will transform to water at 0 degrees Celsius. Okay. The temperature stays at 0 degrees Celsius. I cannot stress that enough. If you take an ice cube at 0 degrees Celsius and add heat to it, it remains 0 degrees Celsius. Latent means hidden. And so the latent heat of fusion is the hidden heat of fusion. When this was first studied and discovered and quantified and so on and so forth, scientists tried to figure out, where does the heat go, right? We are taking this ice cube, which is 0, we're adding heat, but it just changes to a liquid. It doesn't heat up. Normally when you add heat to something, it heats up. That's what I did when I put this water on top of the burner. It heated up. But if you put a burner on an ice cube, it'll melt and you'll have water that's 0 degrees Celsius, okay? So this is what we call the latent heat of fusion, or the hidden heat of fusion. It's the amount of heat needed to cause fusion of a material or melt a material, okay? The other phase change I want to talk about is vaporization. When you take a liquid and say, for example, water, if we throw water on the ground and then we wait for a while, it'll disappear, right? We know it doesn't disappear, it changes into water vapor. It evaporates. So in ordinary English, we call it evaporation. In the sciences, we use this word called vaporization. It sounds like science fiction or Star Trek where something's becoming vaporized, okay? And that's exactly what's happening. It's disappearing. The molecules of steam, right, which we know are H2O, are too small to scatter light, so they technically are invisible to our eyeballs. But water in a container is visible because the molecules are all joined together and it's big enough so that it scatters light. It reflects off the surface and things like that, okay? Now, we need to add heat to this system in order for this to occur. So let's say I have some water here and it's at 100 degrees Celsius. Okay. Remember again, I asked you to memorize 100 degrees Celsius is the boiling point of water. And if I add heat to this, the temperature does not increase. So once you have that pot of boiling water on your stove, and whether it's on simmer or whether it's on high, it might boil more rapidly or a little bit slower, but the temperature of those two waters that I'm talking about that are boiling are both 100 degrees Celsius. Now, in this situation, the temperature is going to be 100 degrees Celsius as the water, slowly boils away and then disappears, right? But what you form over here is steam at 100 degrees Celsius. Okay? It's invisible, so I'll just draw a little cloud to demonstrate that. Okay? And so this is water vapor or steam. Again, the word vapor comes from the word vaporization. We in the English language just call this very commonly steam. Okay? And this is invisible. Okay? This is invisible. And that's going to be 100 degrees Celsius. So again, it's the hidden heat of vaporization or the latent heat of vaporization. This heat is going into the material, but it's not raising the temperature. It's transforming liquid water to steam. Okay? So we've got liquid going to gas. We've got solid going to liquid. These two phase changes need heat to cause that change to occur. Okay? Now there are two phase changes that release heat. And they're the reverse of what I've just said. So if we have steam, for example, you may forget the abbreviations we talked about in chemistry, so I'll just maybe say what these are. So G stands for gas. Okay. So when a quantity of gas changes to liquid, it's going to release heat. The release of heat is shown by this thermochemical equation by showing it on the right side of this kind of like reaction arrow looking thing, okay? So I'm gonna write heat over here, okay? Now, this is most evident in a steam burn. If I were to boil water and I were to spill a small quantity on my hand, it would hurt, I would feel burned, it would be uncomfortable. Okay, especially if it's a large amount, it can cause, second-degree burns, scarring, things like that. Okay. Now, a steam burn is particularly dangerous because when the steam encounters your hand, which is cooler, it's going to condense. When that condensation occurs, it's going to release this heat right here. All right. So that's why a steam burn is very bad. You've all experienced this, you just didn't know this. So if you have a baked potato and you open the foil and that steam hits your hands, you jump back, it hurts really badly, right? Or if you have one of those microwavable noodles or microwave dinners with the plastic covering and you microwave it for a bit, and then you pull that plastic covering off and then the steam hits your hands, it really hurts very badly. The reason why is because the steam is changing to liquid water in a process known as condensation, and that heat is being released to your hands. In addition, that water that's now on your hands is 100 degrees Celsius, which is hot. Okay, so you have two different types of burns. You have the steam releasing that heat, and then you have this hot water that's now on your hands, which is 100 degrees Celsius. Okay, and it's a momentary discomfort if you're opening a potato or an instant meal. Okay, this process is called condensation. And it's something that releases heat. All right. Freezing also releases heat, and it's strange to talk about this. A lot of students don't quite understand this, but that's fine. I'll try to explain it. All right, so here's a chemical reaction. We've got liquid water changing to solid. So this in science is called freezing, and in the English language it's called freezing, so there's no problem there, okay? Heat is released, okay? So again, let me define for you. Remember what the L means. L means liquid. And S here stands for solid. Okay. Now, how do you freeze water? How do you make ice cubes? You take, your ice cube tray, you fill it with water, and then you put it in a freezer, and then you cool it down, right? So it doesn't make sense that it's releasing heat, but that energy has to go somewhere. One way to think about this is that in liquid water, water molecules are tumbling and rotating and vibrating and moving in all different degrees of freedom, okay? You could think of molecules as moving faster and more violently and vigorously in liquid water. But in order to make it change to a solid, they have to give up that energy to now just stay in place and just kind of just wiggle a little bit in a solid lattice known as ice, okay? So liquid water has a lot of energy associated with each water molecule because it can move very, very quickly in many different ways. It can be rotating, it can be moving this way, and also vibrating, okay? In solid water, all that energy is being given up, and then the molecule is just kind of jiggling a little bit, okay? So it makes sense that you have to take away energy to transform something with lots of degrees of freedom and rapid movement and whatnot into something that's now frozen in space, okay? So it has less energy, you see? This is more energy. And in the solid form, we have less energy. Where did that energy go? It got lost to the environment in the form of heat, okay? One last thing I forgot to talk about. Way back here, when I talked about liquid going to a gas, and I said that it requires heat, okay? Now I want to talk about sweating, okay? Or maybe you're at the pool. Okay, so think about it. You're in the water, swimming around, you feel nice and comfortable, and then you're ready to go home, so you jump out of the swimming pool to find your towel and, get ready to leave the pool. You feel cold all of a sudden, okay? Another example is sweating. When you're sweating, there's liquid water that's building up on your skin, and that's evaporating to cool you down, okay? What that's doing is absorbing heat from your body, okay? So let's say we have some water here that's beaded up on our skin. Okay, I hope you can see that in the video here. So here we have some skin, okay? maybe it's on our hand or arm, whatever, doesn't matter. And there we have a little bead of sweat, all right? Or it could be a droplet of water from the swimming pool. Now this water is going to evaporate. And this can occur at room temperature or 30 degrees Celsius or whatever, okay? When that happens, it's going to require heat. Where does this heat come from? It comes from the environment, whatever's touching it. It's touching the skin, so heat is gonna flow into the water. Heat is gonna flow into the water to cause that water to vaporize. The heat's gonna flow out of the skin into the water so that the water can get more kinetic energy, right? To escape the water droplet and change into steam, okay? So in a sense, this is the opposite of freezing, for example. Here we need to add energy to the water molecules to make them move even more vigorously and escape the water droplet and become a gas and go zooming off into space, okay? So we have to provide energy to do that. The reverse process is going to give off energy, okay? So in this video, we've talked about calorimetry. In the lab, we'll explore that more. We've talked about the 3 different ways that heat can flow through objects: conduction in metals, convection in liquids and gases, and radiation in all substances, okay? We talked about the phase changes. There are 4 that you need to remember, okay, that I've outlined here. We have fusion or melting. We have vaporization or evaporation. And the reverse of those are condensation and freezing. Know which ones require heat and which ones give off heat, okay? So that's it for heat and temperature. Hope you enjoyed this video. If you do, consider subscribing, give a thumbs up. Have a great day.